This video is part of a course on food physics, of which this is the theory section. The module, this one, is about heat transfer when phase change is involved. Now, in part one, we provided a qualitative overview of what is meant by a sharp boundary framework to, to, um, to study phase change. The reader is advised to look at that video before this one. And now we'll just dig into the equations. As I just said, we had a bit of a general understanding of what is sharp interface formulation, and we now want to derive the basic equations for sharp boundary with freezing and deep frying as examples. Our task really is how to handle phase change, because the rest of the equations in the regions where phase change has already happened or phase change hasn't happened, those regions, the equations are the same as the normal equations. So as applied to this freezing example, again from literature, in the frozen region, here we just use the heat conduction equation for the frozen part. And then for the unfrozen part, we also use the heat conduction equation. It's where freezing is taking place. That's where we have to do something new. So in this schematic then for freezing process, we have the unfrozen region and frozen region and then the interface. So those three regions. So at the unfrozen region, we just use the normal heat equation. Notice that this is just the normal heat conduction equation with effective properties. So effective properties like thermal conductivity or density, heat capacity, and so on, they are simply for the time being averaged property at the location of the different phases of the material. So just averages. With that, I just use the simple heat equation in the unfrozen part. Likewise, simple heat equation in the frozen part. Now at the interface at some given at some time t, let's say it's at the location S. And so we need to really find an equation for this S. And how we will do that is we'll simply do an energy balance at the interface. So energy balance at the interface is going to look like this. So we're going to do in minus out plus generation equal to change in storage. Just the most common statement of energy conservation. And so at the interface then, if this is my x direction, then because there is only heat conduction, then energy coming in is given by Fourier's law at this location. So energy coming in is thermal conductivity times temperature gradient at the location S. And so what is the unit? Let's make sure we understand this. So this part of it, the first part, K del T del X, has the unit of watts per meter square because it is a flux. and multiplied by A is the area. So multiplied by area, so we get watts. By the way, A is this cross-sectional area this way. So it is this area. Okay, the area that we cannot see here, or we can, if we want, we can do it is this area that is A. Okay, so then this the first term gives me watts that are coming in, and then what's leaving the interface is also the same expression, K times del T del X, or minus K del T del X, always keeping track of direction for the flux, and that's what is leaving. So this is out. So in minus out, again multiplied by area, so it is also watts. And then the generation term is, we can think of heat given off from freezing. So that's the latent heat. So let's see how we can think of it nicely or simply. So let's say there is a thickness of delta M. So let's say an additional mass of delta M freezes over time delta T. So then the rate of freezing is del M over del T, which is equal to area times change delta S, the volume times the density over delta T. Okay, so in other words, this del M del T is in kilograms per second, and that multiplied by latent heat would give me joules per second or watts. So then our kilograms per second is this quantity, which is same as what is written here when we make that delta M go to 0 and we write it for the interface. So d dt of A times S times rho, and this rho again is would be density for water, because it's over the I take that back. This would be density of water multiplied by the fraction of the volume that is occupied by water. And then this lambda has the unit, as I was saying, joules per kilogram. So joules per kilogram multiplied by kilograms per second gives me joules per second watts. So this is also watts, and it matches with the watts here. And so we have everything consistent, and change in storage is going to be 0 because we are doing the balance on at the interface. It has no volume, so it cannot be storing energy. So again, you see these thermal conductivities in these two expressions are for one's for unfrozen, one's for frozen. So two different regions. And now we can simplify this equation. We can drop out the area term and we get this guy. So this is an equation. You notice that K del T del X in the unfrozen part I can find, because I am already solving for temperature in the unfrozen part. Likewise, this part of it, in the frozen part, I am solving the equation in the frozen part. So then these two, the left hand side would be known. So from here I can find S as a function of time. So that will give me the location of interface as a function of time. So the way this problem is set up is I know the location at any time, and then to the left of it I'm going to solve the heat conduction equation in the unfrozen with unfrozen material properties, and to the right I will solve heat conduction equation with frozen material properties. Another example of a food process where the sharp boundary framework can be used is deep frying, or has been used is deep frying. Now I'm not getting into the details of all the equations, and for that the reader is referred to these original work by Farquhar and Ramsey, and there you can find the full details of the equations. Again, just like in freezing, so we'll have three equations for two for the two regions and one for the interface. So let's look at them one at a time. So region 1 is here. So that's where the phase change is yet to happen. So it's wet, and we have the energy and liquid transport there inside. And then region 2 is here, where all the phase change has already happened. So it's the crust or the fried or the dry region. And so here we'll have energy and vapor transport, and then we have the interface. So again, we are not getting into the details of this equation. So the first one is here. So you can see this is our normal heat equation. This is the transient term, and this is the convective term. And this convective term has to do with heat transported by the liquid in the core. That's not our emphasis here. Our emphasis, our focus is that this is a normal heat equation in region 1, where phase change is yet to happen. Likewise, in region 2, we have the normal heat equation again, normal heat equation with corresponding terms, because we also have convection, and convection has a velocity, just like here before. So this velocity is due to pressure driven flow of vapor, because there is evaporation, vapor generation. So of course it generates positive pressure, and so that drives out vapor, and that brings this convection term and the velocity in here. But the point is, this is the normal heat equation with transient term, convection term, and the conduction term. Again, the properties here are effective properties. So in region 1, it's effective thermal conductivity in that region, and likewise in region 2, it's effective thermal conductivity in that region. Okay, so now we want to do the equation at the interface. The equation at the interface, then I'm going to do exactly the same thing. So at the interface, I'm going to say heat in and out and heat taken up by the evaporation, they are related. So in minus out plus generation in this case is we'll see in a second, is equal to change in storage. This is the energy balance that we always write. So let's write the terms. So in term, what's coming in here, that can be due to the conduction, or it can be energy coming in with the flow. So that's the amount coming in. So likewise, the amount going out here is this one, and yeah, it's going out is this one. So in minus out, and then how do I write the generation? And so again, like before, if we think of a small mass delta m that will be evaporated in time delta t, then the rate of evaporation is del m del t, which has an unit of, let's say, kilograms per second, times latent heat lambda for evaporation, which is joules per kilogram. So these kilograms cancel and we get joules per second watt, which is also the unit for the terms of the other two terms. Okay, so this delta m delta t, just like before, I can write delta m delta t to be equal to, and I'm sorry this is getting messy, delta m delta t would be whatever is the cross-sectional area that's in this direction. This is my cross-sectional area, and times delta s, the amount that this interface s, the interface location s moves. So that's the volume times the density divided by delta t. So this comes out to be a rho ds dt. So the term, and times, of course, we also have the lambda term. So del lambda times delta m delta t is this times lambda. And so the point is, you can see the ds dt term. The rest of it is this rho and lambda. They needed to be averaged out over the phases, and there's also some sensible heat that has been included in here. So with this, the point is, we now have an equation for s as a function of time, because these heat flux in and heat flux out are known from the other two equations. Okay, so from there, then we have an equation for s as a function of time. And so this is another example of sharp boundary interface, which is also called interface tracking and the Stefan problem. Now, it could be appropriate to just talk maybe a few minutes about how we solve these equations. So let's talk about two scenarios. One is when you keep the sharp interface, then of course the two heat equations, remember there are three equations, two heat equations and the interface equation. The heat equations are the normal heat equations. So however way you solve them, you can use the same. So implement heat equation in zone 1 and then do the same for zone 2. So zone 1 and zone 2, and then for the interface we solve the interface equation. That one is extra. So in a software like let's say COMSOL, then this would be an added equation solved using their math interface. So this additional equation needs to be solved simultaneously, and coupling this with the other two, yes, it can cause some difficulty. Now, an approximate solution, so this time I'm only talking about numerical approximation, an approximate solution that relaxes the phase change a little, making it over a small temperature range instead of one exact temperature for phase change. So instead of, let's say, 0 degree for phase change, we make it, let's say, between half a degree and 0 degree, minus 0.5 to 0, or some small range. If we distribute the phase change over that small range artificially, it will get rid of the interface equation, and it will still give an answer that's very close, but now you do not have the interface equation, so you can solve it normally. Now, of course, that kind of sharp change does cause some numerical issues, but it can be done. So that is one way to solve these equations, is the approximate the sharp interface into a small range and then implement the same heat equation over the entire domain. So basically what you are doing, let's say if we take the freezing one, then the latent heat of freezing you are distributing over a temperature change, over a small temperature range, I'm sorry, and that way the latent heat you're basically distributing with the sensible heat or the specific heat to make what's called an apparent specific heat. These things are detailed a lot more in the module on freezing, for example. The sharp interface formulation or framework that we have been discussing for phase change is already a simplification, but we can simplify it further in this next section. In this simplification, we ignore variation in temperatures in the domain where phase change has not taken place. So let's say if it's freezing, then in the unfrozen part we say we ignore temperature variation altogether, and in the domain where phase change has taken place we consider it as a pseudo-steady state. So this framework is well known as the pseudo-steady-state method. The popular equations for, let's say, freezing time calculations, they all come from pseudo-steady-state method, and therefore it is an important one. It's an important approximation. We will apply this simplification concept now to freezing. And so we have this material that is unfrozen here and frozen here with air blowing over at, let's say, T infinity, and we're going to follow the same procedure as the less restrictive version of this sharp interface formulation done earlier. Okay, so let's start from the regions. So we have a region 1 where it's unfrozen, and we have region 2 where it's frozen, and we have the interface where phase change is taking place. So recall that the deal with this sharp interface formulation is within the region we use normal heat equation without any change of phase. So let's look at the region 2 first. So region 2, I claim that I can approximate it as steady state. Actually, not I claim, it has been claimed long time ago, and somebody has made this assumption, and that has worked out very well. And so here, why do we think it could be considered a steady state? So latent heat, if you recall, is a lot of heat. So at some point when the freezing, when the interface has reached here, in order for it to go further inside, all of this energy would have to be taken out. And two things. One is the amount of latent heat is a lot of energy. That's the most important part. Latent heat is a lot of energy. And all of that energy has to go through this layer, and that's by conduction, which is a slow process. And also, as the interface moves in, the thickness of this layer increases, which means resistance increases, that further slows down. So a lot of heat and slow removal process, it means the interface will move a bit slow. It moves, of course, because we are trying to find how long it takes to reach this end. So it moves, but it moves slow. So if it moves slow, then for this layer we have one end kind of staying at, let's say, freezing temperature or melting temperature, Tm, and the other end is staying at T infinity. So Tm and T infinity. So if you think of a layer of which two ends are maintained at two different temperatures, then what? It's going to approach a steady state. That's the steady state that we are going to use. Now, remember that this process is not inherently steady, because it, we are interested in how long it takes for the interface to reach the other end. So of course it's not a steady state process, but it's going to reach, this layer is going to reach almost steady, which means the equation for this layer, which would be just heat conduction to start with, I drop the transient term. So the transient term has been removed. So that's all the equation that I need for the frozen region. And the similar logic I'm going to use for the unfrozen region. So recall I was saying that latent heat is a lot of heat. So if all of that heat has to be removed, in other words, quite a bit of heat has to flow out. And that's because it's quite a bit of heat, it's like a heat sink or a heat source in this case. So if that is a significant heat source, it kind of makes it difficult for change in temperature inside. It makes it difficult for change in temperature inside, which means the temperature inside we can assume is not varying. So in region 1, that is the unfrozen region, our heat equation would have been this, but the temperature is not varying with position and therefore not with time also. So we just ignore it completely. So region 1 we completely ignore, region 2 we have this equation, and then at the interface I have this equation. Sorry, this part is overlapping. Let me see. Um, Let me rewrite this one here. Uh, okay, so we're saying the heat flux from region 1 at the same location and region 2 are not the same, which would normally be the same. If you take a location here, then heat flux here is going to be heat flux there. But here at the interface, because there is this heat source, which is the latent heat, it's not going to be the same. So the difference between them is the energy that is coming from the interface movement or the heat given off by the additional amount of freezing. So how do I get this term? A simple way to look at is if I am freezing additional layer dm in time dt. So dm dt is my rate of freezing, kilograms per second, times the latent heat, lambda, is joules per kilogram. So if we cancel the kilogram, then it's joules per second, watts, and I want to have this as a flux. So watts per meter square, A is my cross-sectional area this way, A. So then dm is nothing but the change in the interface ds times the area times density. So ds a rho. So this areas cancel and I guess I get ds dt times rho lambda. So this is energy given off due to phase change. And what this equation does is, because I can calculate this and I can calculate this because I know those regions. In fact, this one is ignored anyway. And because I am solving the steady state, I know this part. So from this, I can calculate what is ds over dt, how the interface moves, what is the speed at which the interface moves. That tells me how long would it take for it to go all the way or to freeze the entire material. Those two equations can now be easily solved. So again, we are in region 2 only, and this is the equation we came up with, steady state. Note that of course we are in Cartesian coordinates, so this is like for a slab. So this thing is a slab, and the solution to this, it's just d squared t dx squared equal to 0. So the solution is t equal to c1x plus c2, right? Just a line. And then if you put in the boundary conditions of Tm here and then T infinity outside, if you do that, then you get the full solution, and I'm skipping that because that's not the goal here. From that, I can, from the solution, the straight line temperature profile, we get the flux. Flux is temperature difference, so Tm minus T infinity divided by two resistances. So what are the two resistances? One is this one, that's this one here, So that's the conductive resistance, and outside it is the convective resistance. So this is convective resistance, and the first one being the conductive resistance. Okay, notice where we have S. S is where the interface is at this time. So this is my flux expression. Of course, the flux changes with time because S changes with time. Now, at the interface, we had this equation where we ignored this term, and so we only have these two terms. And so this is my flux. This is heat flux. And so the flux that I just calculated, I plug that in here, and then I can solve for dSTD. So if we do that, and let's just see, let's do one more step. Okay, so if I plug in that, and we have to keep track of the directions for flux, and I'm not getting into those details now. Let me just write this here: Tm minus T infinity over S over K plus 1 over H is equal to ds dt times rho lambda. Okay, so if I rearrange, I write Tm minus T infinity over rho lambda dt is equal to S over K plus 1 over H ds. Okay, so if we just integrate these two, we get the solution that I'm showing you here. So we solve for S as a function of time. So we get T here as a function of where the location of the interface is. So this is a very, very convenient way to get the time for phase change. So you notice we made it so simple that it can be solved very easily analytically in a closed form, and we can get the time for phase change. In this case, it's for freezing. This is why it has been very popular. What we just did was for a slab like this one. This is the one we just derived. Now this can be extended to other geometries like a long cylinder. So it has to be long cylinder. So it's 1D. So the freezing is happening only in this direction. Or for a sphere where the heat is moving only in this direction. And so we can get similar formulas. How long does it take the time for freezing in this case for a radius r, or freezing here for a sphere of radius r? And likewise, this was for freezing, and then we can do the same for, let's say, freeze drying and other areas where we can make this kind of approximation of not just a sharp boundary phase change, but also this pseudo steady state process. Now, if you are wondering where this other equation came from, or some more details of the derivations of the slab equation, please refer to the video on freezing. Coming back to kind of ending this section, so what we did is we talked about this sharp interface formulation in its general form, and then a more specific form where it's further simplified with the pseudo steady state assumption. And the goal of these kinds of formulations is to get quick estimate of times for phase change. So this is T is the time for phase change. and these equations shown here are for freezing, and we can have similar ones, let's say, for freeze drying and other phase change processes.